In this video, we will discuss how to implement a very simple cache and also what kind of possible improvements we could envision for making caches even more efficient. So once more, a cache is a small device that sits in between the CPU and the memory. Its input is an address and its output is some kind of data as well as an indication of whether or not the data can be trusted. So we're going to design this pink box here in a simple way and gradually make the implementation more and more efficient. So in this course, you're going to see lots of letters and symbols and so on. So let's straighten out what I mean with all these symbols. So typically when I write K in this course, it could be a small k or sometimes a large K as well. I typically mean 2 to the power of 10, so it's a kilo. When I write capital B, I mean byte, 8 bits, and when I write a small b, I mean bit. This typically symbolizes a 32-bit address with the most significant part and the least significant part of the bits. And this is part of the input for the cache. This symbol I normally use for just to show ordinary memory. So this is memory that contains some data. Depending on what address you apply to it, you're going to select one of these rows and read that out from that memory. And when we talk about caches, we typically are talking about static RAM, SRAMs. So the name of the game here is to design a cache that contains 4 kilobytes of data, and it's a direct map cache. That means 4 kilobytes of data, and we assume now that we store 4 bytes of data, so a word of data in each of these entries. So this is 4 bytes of data. That means that we need 1K of these entries in our SRAM. So we have 1K entries, each storing 4 bytes of data. Then we have some address tag, and we have some kind of valid bit stored right here. In order for us to choose the piece of information that we're interested in, we need an index function. The goal of this index function is not to find 1 out of 28 pages. It is to find 1 out of 1K entries in this SRAM. And depending on what index function you apply here, you're going to read out all the information that's stored in that place. You're going to read out 4 bytes of data, a word. In this example, you're going to read out some address tag and the valid bit. So this is read from the SRAM location identified by the index function. So the first question here is, how many index functions are needed in order for this cache to work in the way I described? And you will check the box 10 here, because 2 to the power of 10 is 1K. So God has been very kind to us that when we would like to deal with a binary number system. So the same number of fingers you have in your hand, that number of bits is needed to represent 1K unique values. If you would like to represent 1 meg unique values, you need twice that. So you need 20 bits. 1 gig, you need 30 bits and so on. So that saves you a little bit from counting 2, 4, 8, 16, 32 and so on your fingers. So 10 bits, 1K. Okay, so that's how many bits we need on this index function. Now the question is, what is a good index function? You remember what was a bad index function in the address book example. If you're so smart, can you help me figure out what would be a good index function here? Should we use the most significant part of an address? Should we use the middle part of an address? Or should we use the least significant part of an address when we pick those 10 bits that we need for the index function? And the reason we would like to pick the least significant part of an address, or from at least that end of the address, is that's where you have most uniform distribution of values. So these values at the least significant part are more likely to change rapidly throughout the execution, while the most significant bits may not change at all. Let's say that you haven't fully populated the memory in your system, then these most significant bits will have the same value all the time. If you use them as an index function, you would always index to the same part of the cache, and you would have grossly misused the capacity of this very valuable piece of storage where you would like to store your favorite data. So that's what the cache looks like. So let's now really design a real cache given those kind of input information. So we have once more, we input address, most significant, least significant, and we have the SRAM array stored right here. Since we are storing 4 bytes of information in each of these entries, and these 4-byte entries are aligned, when we design a cache, we actually don't need to worry about the 2 least significant bits of the address, because typically an address in a computer uniquely identifies a byte in memory, but the name of the game here for this cache was to find the word. So we're just going to toss these 2 least significant bits over our shoulder when we design our caches. And those bits are only going to be used by the CPU itself if it uses some byte addressable kind of instruction. Then we're going to use the next 10 bits, as you correctly said before, for the index function on this cache. In that place, in the place in SRAM identified by these 10 index bits, we're going to read out the value stored there. And in order for us to determine if the piece of data we're looking for is indeed in the cache, we're going to compare the 20 address tag bits with the part of the identifier that wasn't used for the index function. So the same way we drop the T in Thomas in the address book example, we're going to drop all the bits we used for the index function when we store the value of the address tag. So only 20 bits stored here compared with the 20 bits of the address we access. And then we have a valid bit that this bit just says that this place in the cache has been initialized at all. So we make sure that that bit is set. If this comparison, 20 bits compared with 20 bits, is true, and the valid bit is set, then we're going to produce the single hit signal we need as an output, and the data stored in that location, that word of 4 bytes, we're going to send back to the processor. So the memory overhead for this implementation, you look at how many bits you store how many useful bits you store in the cache compared with how many useless bits or extra overhead bits you store. So we're going to compare. We have 32 useful bits and we have 21 of these extra metadata stored here. So the memory overhead for implementing this cache is 66%. The latency for accessing this cache is the latency it takes to make an SRAM access to get all the data out, and the time it takes to do this comparison and to go through an AND gate in this example. So there you have it. That's how you implement the cache. You provide an address, back comes a hit signal, and back comes the data that you're looking for. If it's a hit, you use the data provided by the cache. If it's not a hit, you use the data from the memory, and you may also store it in the cache to be used at a later point in time. So in the next video, we're going to talk about how to judge an architecture and see, so how we can tell a good cache from a bad cache.